Hello everyone, this is the Senior Design Live demo of the Rain Energy Harvester. This project has the main objective of converting the mechanical energy from rainwater to electrical energy, which can be used to power small-scale devices. It is designed so that it can be easily connected to a gutter of a home and repurpose the rainwater coming from the roof of the building. The Rain Energy Harvester serves as an alternative, renewable energy source for simple applications.
A hose is used to fill the 10-foot pipe structure and focus a jet of water into the turbine's paddles, causing the turbine to rotate. This causes a shaft connected to the turbine to rotate as well as a motor that is connected to this shaft using a 1:2 gear set ratio. The signal generated by the motor is passed through our PCB and onto a USB outlet. A switch is used to turn on the outlet, and another switch is used to connect a 9-volt battery to components that are used for monitoring the signal generated by the motor. Here we have the text mode, which displays all of the information in text form. By pressing a button, we can swap over to the graphing mode, which displays the power generated in a line graph form.
Alright, so these 4 connections are where our motor connects to our 2 full bridge rectifiers, which sends the current to our sensor, which reads voltage and current. Then that goes into our voltage regulator, which regulates it down to 5 volts, which sends it to our sensor 2, which also reads the voltage and current. And then we've got our output pins over here, which is where sensor 2 sends the current. And we've got our VCC voltage regulator, which regulates a 9-volt battery down to 5 volts to supply power to our sensors and our MCU and our LCD screen. And we've got our MCU here on the back. And we've got our connections for the LCD here on the side. And also we've got a button to switch the screens.
Here is the system in action. As you can see, the turbine is spinning due to the water. The gears here are rotating, causing the motors to generate electrical power. Here is the LCD screen displaying the measurements in text and line graph form.
For this demonstration, we're using an USB LED light as the output device. As you can see, the turbine is spinning and the USB outlet switch is off at the start. We turn on the switch and we can see the LED light turning on, and the power statistics are shown in the display. We flip the switch between on and off here to show that the USB outlet is properly providing power to the LED light. Next, we switch to the graph mode on the display to show how the power behaves related to the brightness of the LED. For this next section, we purposely turn the water off and turn it back on to show in the graph how the power goes back to meet the power demand of the load.
For this demonstration, we will be using a wireless charger to charge our phones. The turbine is spinning, and here is our phone charger, but it is not charging because the USB output switch is off. Now we will turn on both the USB output and the LCD switch. The phone is now indicating it is being charged. The power dissipates until the phone stops charging. The power sharply rises, then the phone starts to charge again. Here are the text measurements provided by the LCD. Now we swap to graph mode. The power decreases as the phone is charging. Then the charger stops charging. Power spikes up to be able to charge the phone again.
Okay, so this is our fan demo where we'll be powering a USB fan, and we swapped out our pipe for a hose so we can get better RPM. So we flip the switch to turn on the outlet, and then we press the button on the fan to turn it on. And here we can see that it works. So here are the values being read due to the fan being at the outlet. And we see that at the outlet it's about 1.2 watts. Then let's switch over to the power graph. And here we find that the power being generated is actually around 2 watts. So here we turn off the fan momentarily so you can see the drop to 0. And then we turn it back on, and that shows a steeper turn on power required.
The three main specifications that will exhibit are the turbine speed, the power generated coming from the motor, and the output power coming from the USB outlet. We also have the regulation efficiency as a backup specification that we can show during the final demo. We are expecting a minimum constant turbine speed of 120 RPM and a maximum of 350. It can be higher than 350, but this greater value is not needed to maintain system performance. For the power generated, we're expecting a minimum of 0.25 watts and a maximum of 5 watts. The output power will be a minimum of 0.1 watts or 100 milliwatts with an expected maximum of 4 watts. The regulation efficiency is expected to be higher than 50%.
For RPM accuracy testing, we decided to use our hose with an adjustable nozzle directly, instead of using the pipe, so that we could more easily change the RPM of the turbine and better ensure the accuracy of our measurements. On the left you can see we are using a tachymeter, along with some black tape on the turbine to measure the RPM. On the right you can see the LCD screen displaying the RPM that has been calculated using power measurements. Both of these videos were recorded simultaneously. Over time we change the RPM, and the values that are displayed on the LCD screen can be seen to closely and consistently match the values measured by the tachometer. Due to the voltage limits of the motor and the sensors, we can only ensure RPM reading accuracy up to around 450 RPM. This table shows the RPM values calculated and displayed on the LCD and the values measured by the tachometer over the course of about 30 seconds. This line graph uses the values from the previous table. These measurements closely line up with one exception at 6 seconds. We believe this to be an error from the tachometer, as it occasionally displays incorrect values if there is an issue with the lighting.
To prove the sensor readings of the DC power generated by the motor is accurate, a voltmeter reading and LCD display of the voltage were compared. The voltmeter is connected to the test pad at the full bridge rectifier and ground. As shown, both the voltmeter and M voltage value displayed on the LCDs were very close to each other, even at varying RPMs. The current of the power generated could not be measured because of the way the circuit would have to break on the PCB. However, current of the power generated were measured previously in the lab, validating accuracy.
To prove the accuracy of the second shunt sensor, the voltage of the USB outlet is being measured using a multimeter. Once water has been applied to the turbine, we see the voltage quickly rise from 0 to 5 volts. The outlet is regulated at 5 volts to be compatible with USB 2.0 devices. We stop the flow of water for a few seconds and then restart it again to prove that the readings are accurate. Continuing the shunt sensor testing, the current of the USB outlet is being measured using a multimeter and the USB current value on the LCD screen. To measure the current, probes of the multimeter were placed between the USB's VBus node and the USB light was used as a load. The current readings on the multimeter were found to closely and consistently match those of the USB current values on the screen.
The first output device we use to show our project performance is an USB LED light. Here you can see the data we collected during this test. The generated power and output power follow the same pattern with a difference that remained mostly constant during this test. We also measured the regulation efficiency values when using the USB LED. For the whole duration of this test, the regulation efficiency remained above the 50% mark, which satisfies our specification.
The generated power and outlet power values were recorded from the LCD screen during the wireless charger demo video. Both the generated power and outlet power were in the range noted by the specification table. The generated power and outlet power were plotted on a line graph and shared the same shape but with the outlet power at a lower offset. The graph has peaks of power at an interval, proving the LCD generated power graph is displaying properly and proving the charger becoming ready to charge at the peak and discharging until no longer chargeable. The regulator efficiency was also recorded from the video and plotted onto a line graph. The regulator efficiency was constantly between 62 to 66%, averaging an efficiency of 64.574%, meeting the specification requirements of being a minimum of 50%.
So here we have the measurements for the USB fan. We compiled the generated power and outlet data over 10 seconds and graphed it for when the USB fan is plugged into the outlet. We see that the power generated at the motor is around 2 watts, while the power reaching the outlet is around 1.2 watts. Then we also graph the regulation efficiency over 10 seconds, and we find that the efficiency is around 58.93% on average.
This table and graph show the voltage values measured by the first shunt sensor located after the full bridge rectifiers and the multimeter used in the demonstration. This proves that the sensor is measuring voltage accurately. This table and graph shows the voltage values measured by the second shunt sensor located at the outlet of the system and the multimeter used in the demonstration. This sensor has sharper changes than the multimeter. We believe this to be due to a difference in the refresh rate between them when updating. This table and graph show the current values measured by the shunt sensor and the multimeter with a USB LED connected as the load. The measured values closely match, proving that this sensor is accurate.